Lie down comfortably and let your eyes gently close. Feel the weight of your body sinking softly into the mattress, each muscle releasing the tension accumulated throughout the day. Tonight, as you rest, we will explore together something that physicists have been quietly debating for the last 100 years. A question so fundamental that it challenges everything we think we know about the world around us. When you look at the wall of your room, it appears solid. When you touch the pillow beneath your head, it feels real, present, unquestionable. But what happens when we are not looking? What exists when no one is observing? For decades, physicists assumed that reality was simply there, independent of us, like an empty stage waiting for actors. Particles occupied definite positions. Objects had concrete properties. The universe followed its course, indifferent to our presence. That certainty began to dissolve in the early decades of the 20th century, when experiments with subatomic particles revealed behaviors impossible to explain with classical physics. Electrons seemed to be in multiple places at once. Photons behaved like waves until they were measured when they suddenly became particles. The very nature of matter seemed to depend in some strange way on the act of observation. And there is a detail in this story that remains open, something we will explore later when we are more relaxed and ready to contemplate its implications. For now, breathe deeply and let this idea settle gently in your mind, like a leaf slowly descending onto the surface of a still lake. There is no rush to understand everything. Tonight is about rest, about gentle curiosity, about letting profound questions float around you while your body prepares for sleep. Quantum physics was born from anomalies. In the early 20th century, scientists began to realize that the rules governing the visible world, planets orbiting stars, apples falling from trees, waves breaking on the shore, simply did not work when applied to the invisible world of atoms. It was like discovering that the traffic laws you follow in your city do not exist in another, where cars can occupy two streets simultaneously and only choose one when a traffic officer looks at them. The first physicists to confront these oddities reacted in different ways. Some, like Niels Bohr, accepted that reality at the quantum level was fundamentally different from everyday reality, and that perhaps we should not even ask what a particle really is when we are not measuring it. Others, like Albert Einstein, resisted. Einstein spent the last decades of his life trying to prove that quantum mechanics was incomplete, that there must be a deeper, more sensible reality hidden beneath those strange equations. The history of this dispute is fascinating not for its conflicts, but for its persistence. Almost a century later, we still have no consensus. Laboratories around the world continue to conduct increasingly sophisticated experiments, testing the limits of what quantum mechanics predicts. And the results consistently confirm the strangest predictions. Reality at the fundamental level seems to resist our intuitions about what it means to exist. Tonight, we will not resolve this debate. No one has resolved it yet. But we can walk together through its conceptual landscapes, observing the ideas as one observes distant mountains at dusk, without the need to climb them, simply appreciating their shapes on the horizon. We will talk about what it means to say that something is real. We will explore experiments that challenge common sense. We will consider what different physicists have proposed as explanations. And along the way, you can simply relax, letting the words flow, allowing sleep to arrive when the time is right. Your only job now is to rest. The universe will continue to exist, or not exist, depending on how we interpret physics, regardless of whether you are awake or asleep. So close your eyes, release your shoulders, and let me guide you gently through this contemplative journey into the nature of reality. Before we go deeper into this exploration of what reality might or might not be, I want to take a quiet moment to thank you for being here tonight. If you find these journeys through physics and cosmology helpful for relaxation, If you enjoy this way of exploring deep questions while preparing for sleep, please consider subscribing to the channel and leaving a like on this video. It helps others find these nighttime explorations, and it allows me to keep creating them for you. If you know someone who struggles with sleep, or someone who loves contemplating the mysteries of the universe, consider sharing this with them. These stories are made for quiet moments, for those hours when the mind needs something meaningful but gentle to hold on to. And whenever you need it, come back. Let this become a familiar companion in those still hours when sleep feels distant. That is what it is here for, to guide you softly into rest, night after night, whenever you need it. Now let us continue our journey into the heart of quantum strangeness. There is something reassuring about the physical world. You knock on a wooden table and it responds with a solid sound. You press your hand against a wall and it pushes back. You stand on the ground and it holds you up without question. From the moment we are born, we learn to trust the solidity of things. Objects have edges, surfaces have textures. Matter occupies space in a definite, reliable way. This trust in solidity is not misplaced for everyday life. When you walk across a room, you do not fall through the floor. When you pick up a glass, it does not pass through your fingers. The world behaves consistently at the scale of human experience, and that consistency allows us to navigate through life without constantly questioning whether things are real. But physics tells a different story when we look closely. The wooden table that feels so solid is in fact mostly empty space. Atoms, which make up all matter, consist of a tiny nucleus surrounded by electrons. If you could enlarge an atom to the size of a football stadium, the nucleus would be a small marble at the center, and the electrons would be specks of dust somewhere in the stands. Everything in between would be emptiness. So why does the table feel solid? Why does your hand not pass through it? The answer lies not in the presence of matter, but in the presence of forces. Electromagnetic forces between the electrons in your hand and the electrons in the table repel each other. When you touch the table, you are not really touching matter at all. You are feeling the resistance of electromagnetic fields pushing against each other. The sensation of solidity is an electromagnetic illusion, a dance of forces that creates the impression of substance where there is mostly void. This realization alone is enough to unsettle our common sense understanding of reality. But it is only the beginning, because when physicists looked even more closely at those electrons, at those tiny specks supposedly orbiting the nucleus, they found something far stranger than empty space. They found that the electrons did not behave like tiny balls of matter at all. They did not have definite positions until someone tried to measure them. They existed in what can only be described as a cloud of possibilities, a smeared-out probability distribution that only collapsed into a definite location when an observation was made. Imagine a coin that is not heads or tails until you look at it. Not spinning, not uncertain in the ordinary sense of the word, but genuinely neither heads nor tails, existing in a state that includes both possibilities simultaneously. That is, in a simplified way, what quantum mechanics tells us about particles before measurement. They do not have definite properties. They exist in superpositions of all possible properties, and only when we measure them do they seem to choose one. This is not a limitation of our knowledge. It is not that the electron has a position and we simply do not know what it is. According to the standard interpretation of quantum mechanics, the electron genuinely does not have a definite position until it is measured. The uncertainty is not in our minds. It is in the fabric of reality itself. Let this idea rest gently in your thoughts as you lie here. The floor beneath your bed, the ceiling above you, the air around you, all of it is made of particles that, at the deepest level, do not behave like the solid, definite objects we imagine them to be. They shimmer with quantum uncertainty, existing in superpositions of states, only settling into definite properties when interactions occur that we might call measurements. And yet, despite this underlying strangeness, the world appears solid. The floor holds you up, the ceiling stays in place. The quantum fuzziness of individual particles somehow averages out at larger scales, producing the reliable, predictable world of everyday experience. The question of how this happens, how the strange quantum world gives rise to the ordinary classical world, is one of the deepest puzzles in physics. It has a name, the measurement problem, and it has no universally accepted solution. For now, simply notice how this changes the picture of reality. The solid world is not solid. The definite world is not definite. Beneath the surface of ordinary experience lies a realm where the rules are different, where particles dance in clouds of probability, where the act of looking seems to matter in ways we do not fully understand. And somewhere in that dance, in that interplay of possibility and observation, lies a question that physicists have been circling for a century. What is reality made of, really? What exists when no one is watching? In the history of physics, there are experiments that confirm what we already believe, experiments that refine our measurements, and experiments that shatter our understanding of the world. The double-slit experiment belongs firmly in the third category. It is simple to describe, easy to perform with modest equipment, and yet its implications are so profound that physicist Richard Feynman once said it contains the only mystery of quantum mechanics. Imagine a barrier with two narrow slits in it, and behind the barrier, a screen that can detect where particles land. Now imagine shooting tiny particles, electrons, photons, even molecules, at the barrier, one at a time. Each particle passes through the barrier and eventually hits the screen somewhere, leaving a small mark. After many particles have been fired, a pattern emerges on the screen. If particles behaved like tiny balls, you would expect two clusters of marks on the screen, one behind each slit. Particles that went through the left slit would land in a region behind the left slit. Particles that went through the right slit would land in a region behind the right slit. Simple, intuitive, exactly what common sense predicts. But that is not what happens. Instead, the screen shows an interference pattern, alternating bands of many marks and few marks, exactly like the pattern you would see if waves were passing through the slits and interfering with each other. Where the crests of two waves meet, they reinforce each other, creating a bright band. Where a crest meets a trough, they cancel out, creating a dark band. This wave-like interference pattern appears on the screen, even though we are firing particles one at a time. Think about what this means. Each particle is fired individually. There is only one particle in the apparatus at any given moment. And yet, each particle somehow interferes with itself, as if it passed through both slits simultaneously, as if it were a wave spread out in space rather than a localized ball of matter. The particle does not choose one slit or the other. It seems to explore both possibilities at once, and only when it hits the screen does it manifest in a single, definite location. Now here is where the strangeness deepens. What if we try to catch the particle in the act? What if we place detectors at the slits to see which slit each particle actually goes through? When we do this, the interference pattern disappears. The particles start behaving like tiny balls, going through one slit or the other, producing two clusters on the screen exactly as common sense would predict. The act of observing which slit the particle goes through seems to change the particle's behavior. Observation seems to matter. Let that settle into your awareness as you breathe slowly. The simple act of looking, of gathering information about which path the particle took, changes the outcome of the experiment. When we do not look, the particle behaves like a wave, exploring multiple possibilities simultaneously. When we do look, it behaves like a particle, following a single definite path. Reality seems to respond to whether or not we are paying attention. This is not a matter of disturbing the particle with our measurement devices. Physicists have designed increasingly clever experiments to minimize any physical disturbance, and the result is always the same. It is not the physical interaction of measurement that matters. It is the acquisition of information. If information about the particle's path exists anywhere, even if no human ever looks at it, the interference pattern disappears. Reality seems to care about whether information is available, not about whether anyone actually looks at it. Some physicists interpret this as evidence that consciousness plays a special role in physics, that the mind of the observer somehow collapses the quantum superposition into a definite state. Others reject this interpretation, arguing that consciousness is not special, that any interaction complex enough to count as a measurement will produce the same effect. The debate continues, unresolved, a century after the experiments first revealed this strange behavior. What is clear is that our naive picture of reality, where particles have definite properties whether or not we look at them, does not survive the double-slit experiment. Something stranger is going on. The particle is not simply a tiny ball of matter following a definite path. It is something else, something that does not fit neatly into the categories of everyday experience. Wave and particle, possibility and actuality, observation and reality. These concepts intertwine in quantum mechanics in ways we are still struggling to understand. As you rest here, you need not solve this puzzle. No one has solved it definitively, but you can let the strangeness wash over you gently, like a slow tide. The world is not what it seems. Beneath the surface of ordinary experience, something mysterious is unfolding. And that mystery is not a failure of physics. It is what physics has discovered. The equations work, the predictions are confirmed. The strangeness is not a bug in our theories. It appears to be a feature of reality itself. We use the word real casually in everyday life. The table is real. Your thoughts are real. That dream you had last night was not real. We sort experiences into categories. Real and unreal, actual and imaginary, objective and subjective, as if the distinction were obvious. But quantum mechanics forces us to examine these categories more carefully. What do we actually mean when we say something is real? One common definition is that something is real if it exists independently of our observations. The moon is real because it continues to exist even when no one is looking at it. This is called realism, the view that there is an objective world out there with definite properties, regardless of whether anyone is measuring or perceiving it. For most of human history, and for most of the history of science, realism seemed obviously true. Of course, the world exists independently of us. Of course, particles have positions even when we are not looking. What else could possibly be the case? Quantum mechanics challenges this assumption. If particles do not have definite properties until they are measured, then in what sense do they exist independently of observation? If an electron has no definite position until someone detects it, is there really an electron there at all before the detection? Or is there just a mathematical object, a wave function, that describes probabilities with no underlying reality until an observation occurs? Different physicists have different answers to these questions, and their answers define different interpretations of quantum mechanics. The Copenhagen interpretation, developed by Niels Bohr and his colleagues in the 1920s, essentially tells us to stop asking what is really happening between measurements. According to Copenhagen, quantum mechanics is a tool for predicting the results of measurements, and questions about what particles are doing when we are not measuring them are meaningless. There is no hidden reality beneath the equations. The equations are all there is, and they tell us probabilities, not definite facts. Einstein found this deeply unsatisfying. He famously asked whether the moon exists only when someone is looking at it. He believed that a complete physical theory should describe reality as it is, not just predict measurement outcomes. He spent years searching for a deeper theory that would restore realism to physics, that would explain quantum mechanics as an approximation to some more fundamental, realistic description. He never found it. Other physicists have proposed different interpretations. The many worlds interpretation, developed by Hugh Everett in the 1950s, takes the opposite approach from Copenhagen. Instead of saying that reality is less than what the equations describe, many worlds says reality is more. Every time a quantum measurement occurs, the universe branches into multiple copies, one for each possible outcome. In one branch, the electron goes through the left slit. In another branch, it goes through the right slit. Both outcomes are equally real, but they occur in separate, non-interacting branches of a vast multiverse. There is no collapse, no special role for observation. Everything that can happen does happen somewhere. The many worlds interpretation preserves realism. There is a definite reality. It's just much bigger than we thought, but at the cost of proposing an infinite number of parallel universes that we can never observe or test. Many physicists find this price too high. Others find it elegant, even beautiful. There is no experiment that can distinguish between many worlds and Copenhagen, so the choice between them is often made on philosophical or aesthetic grounds rather than empirical ones. There are other interpretations too. Pilot wave theory, which restores definite particle positions by adding hidden variables. Relational quantum mechanics, which says that properties are not absolute, but exist only relative to other systems. Cubism, which treats quantum mechanics as a user's manual for any observer's beliefs rather than a description of objective reality. Each interpretation has its advocates and its critics. None has achieved consensus. What this situation reveals is that physics, for all its precision and predictive power, does not settle the question of what is real. The equations work. The predictions are confirmed by experiment. But the equations are compatible with radically different pictures of reality, and physics alone cannot tell us which picture is correct. The question of what is real turns out to be partly a question for philosophy, not just physics. As you lie here in the quiet darkness, you might notice that this uncertainty is not disturbing, but oddly liberating. The world is stranger and more open than we usually assume. The confident materialism that says reality is just particles bouncing around according to fixed laws turns out to be one interpretation among many. Other interpretations are equally consistent with the evidence. The question of what is real remains genuinely open, genuinely mysterious, even at the frontier of human knowledge. And perhaps that openness is appropriate. Perhaps reality is not the kind of thing that can be pinned down in a simple formula or a neat category. Perhaps it is more fluid, more relational, more dependent on perspective than our everyday intuitions suggest. You do not need to choose an interpretation tonight. You can simply rest in the openness, letting the question float gently in your awareness, a companion to your breathing, a soft mystery accompanying you towards sleep. There is another feature of quantum mechanics that challenges our understanding of reality, and it has to do with connection. We normally think of objects as separate, independent entities. The book on your shelf has nothing to do with a rock on Mars. They are distinct objects, far apart in space, with no influence on each other. This assumption of separability, that distant objects are independent, seems so obvious that we rarely question it. Quantum entanglement shows that this assumption is wrong, or at least incomplete. When two particles become entangled, which happens when they interact in certain ways, they form a single quantum system that cannot be fully described by treating the particles separately. Measure one particle, and you instantly learn something about the other, no matter how far apart they are. The correlation between them is stronger than any classical explanation allows. Here is how it works in a simplified example. Imagine two particles that are created together in such a way that their spins are correlated. Spin is a quantum property that can be measured in different directions, and for entangled particles, the measurement outcomes are connected. If you measure one particle and find that its spin is up in a certain direction, the other particle will be down in that same direction instantly, regardless of how far apart the particles are. At first, this might not seem strange. Perhaps the particles simply had definite spins all along, decided at the moment of creation, like a pair of gloves packed in separate boxes. If you open one box and find a left glove, you know the other box contains a right glove. No mystery there. But quantum mechanics says the particles do not have definite spins before measurement. They exist in a superposition of both possibilities until one of them is measured. The measurement of one particle does not just reveal a pre-existing property. It seems to instantaneously affect the other particle, causing it to have a definite spin that it did not have before. Einstein called this spooky action at a distance and argued that it showed quantum mechanics must be incomplete. There must be some hidden variables, some deeper level of description that explains the correlations without requiring instantaneous influence. In 1964, physicist John Bell devised a way to test this. He showed that if hidden variables exist, the correlations between entangled particles must satisfy certain mathematical inequalities. If quantum mechanics is correct, and there are no hidden variables, the correlation should violate these inequalities. The experiments have been done many times with increasing precision. The results consistently violate Bell's inequalities. The correlations between entangled particles are exactly what quantum mechanics predicts, and they cannot be explained by any theory that assumes particles have definite properties before measurement. Either information is traveling faster than light, which would violate relativity, or the particles do not have definite properties until they are measured. Most physicists accept the second option, strange as it is. What this means for our understanding of reality is profound. The universe is not made of separate, independent parts. At the quantum level, distant particles can be connected in ways that defy our intuitions about space and time. The whole is not just the sum of its parts. There are correlations between parts that cannot be explained by any properties the parts have individually. Some physicists see this as evidence that reality is fundamentally holistic, that the universe is a single interconnected whole, and the appearance of separate objects is an illusion. Others are more cautious, noting that entanglement does not allow faster-than-light communication. The correlations are real, but you cannot use them to send signals. The interpretation remains debated, but the experimental facts are clear. Entanglement is real, and it reveals a kind of connectedness in nature that classical physics never imagined. As you rest here, breathing gently, you might notice that you too are connected to the world around you in ways you rarely think about. The atoms in your body were forged in stars. The air you breathe has circulated through countless lungs before yours. The photons from distant galaxies have traveled billions of years to reach your eyes. You are not separate from the universe. You are part of it, woven into its fabric, participating in its ongoing dance. And at the quantum level, that connectedness goes even deeper. The particles that make up your body are not isolated specks of matter. They are nodes in a vast web of correlations, entangled in subtle ways with particles everywhere. The boundaries between you and the world are not as sharp as they seem. The sense of being a separate self, distinct from everything else, is a useful simplification. But it is not the whole truth. At the deepest level, everything is connected. Let that sense of connection accompany you as you drift towards sleep. You are not alone in the darkness. You are part of something vast and interconnected, a universe that holds you within its web of correlations. The strangeness of quantum mechanics is not cold or alienating. It is intimate. It reveals that separation is an illusion, that connection runs deeper than we know. We have traveled far tonight, from the apparent solidity of everyday objects to the quantum fuzziness that underlies them, from the double-slit experiment to entanglement, from competing interpretations of reality to the deep question of what it means for something to be real. And through all of this, one theme has recurred: uncertainty. Physics, the most precise of sciences, has led us not to certainty, but to profound questions that remain unanswered. For some people, this is disturbing. We want answers. We want to know what the world is really made of, how it really works. The idea that physicists, after a century of effort, still do not agree on what quantum mechanics tells us about reality can feel like a failure, a gap that needs to be filled. But there is another way to see it. Perhaps the uncertainty is not a failure, but a feature. Perhaps reality is genuinely open, genuinely strange, not reducible to the simple mechanical picture that classical physics once suggested. Perhaps the universe is more like a poem than a machine, rich with meaning, open to interpretation, never fully captured in any single description. Philosophers have long distinguished between different kinds of uncertainty. There is uncertainty that comes from lack of knowledge. You do not know what is in a closed box, but the contents are definite, and you could find out by opening the box. This is epistemic uncertainty, uncertainty in the mind. Then there is uncertainty that seems to be built into reality itself. The electron does not have a definite position, not because we do not know it, but because there is no definite position to know. This is ontological uncertainty, uncertainty in the world. Quantum mechanics suggests that ontological uncertainty is real. The fuzziness is not in our knowledge, but in nature. This does not mean that science is useless or that anything goes. Quantum mechanics makes precise predictions that have been confirmed to extraordinary accuracy, but the predictions are probabilistic, and the underlying reality, if there is one, remains elusive. Learning to live with this kind of uncertainty is perhaps a skill for our times. We live in a world that often demands certainty, that rewards confident answers and punishes ambiguity. But the universe itself, at its deepest level, does not provide the certainty we crave. The most fundamental questions: what is real, what exists, how observation relates to reality, remain open. And perhaps that openness is not a problem to be solved, but a condition to be accepted. There is a certain peace that comes from accepting uncertainty. When you stop demanding that the world be simpler than it is, when you stop needing to have all the answers, you can relax into not knowing. The questions become companions rather than burdens. The mystery becomes a source of wonder rather than anxiety. And here at the edge of sleep, that acceptance is especially fitting. Sleep itself is a surrender of control, a letting go of the waking mind's constant effort to understand and manage. In dreams, the ordinary rules dissolve. Time becomes fluid. Space becomes malleable. The impossible becomes ordinary. Sleep is a nightly reminder that consciousness can take many forms, that the familiar world of waking experience is not the only way to be. Perhaps quantum mechanics is telling us something similar. The familiar world of definite objects and clear boundaries is not the only way reality can be. Beneath the surface, something stranger is happening, something that does not fit into our ordinary categories. And we can approach that strangeness with curiosity rather than fear, with openness rather than demand. You do not need to understand everything. You do not need to resolve the debates between physicists or choose the correct interpretation of quantum mechanics. You can simply rest in the openness, letting the questions float gently like stars in the night sky, beautiful, distant, not needing to be grasped. And so we arrive at the end of this journey, though perhaps end is not quite the right word. We have not reached a destination so much as rested at a lookout point, taking in a view that extends further than we can see. The questions we have explored tonight, what is real, what exists, how observation relates to reality, are not questions with neat answers waiting to be discovered. They are questions that have accompanied humanity for millennia, and they will continue to accompany us, evolving as our understanding deepens. What physics has given us is not certainty, but something perhaps more valuable, a glimpse of how strange and wonderful the world truly is. The solidity we take for granted is electromagnetic repulsion. The particles that make up everything are clouds of probability. The universe is entangled in ways that defy our intuitions about space and separation. And the question of what is real, what truly exists, remains genuinely open. You can carry this with you as you drift into sleep, not as a burden, but as an invitation to hold the world more lightly, to recognize that your everyday certainties are useful simplifications, not ultimate truths, an invitation to wonder, to remain curious, to see the mystery not as something to be solved, but as something to be appreciated. The pillow beneath your head is made of atoms that are mostly empty space, held together by forces shimmering with quantum uncertainty. And yet it supports your head, soft and real in the way that matters for sleep. The darkness around you is not empty but filled with fields and fluctuations, a quantum sea that underlies everything. And you, lying here, breathing gently, are part of all of this, a pattern of matter and energy that has learned to ask questions about itself. Rest now. Let the questions dissolve into the quiet. Let your body sink into the bed. Let your thoughts soften. Let sleep come when it is ready. The universe will continue its strange dance, whether or not you understand it. And you, part of that dance, can simply be here, now, in this moment, which is perhaps the only reality that truly matters. Good night. May your sleep be deep, your dreams be gentle, and your rest bring you peace. And when you wake, the world will still be here, still strange, still beautiful, still inviting you to wonder.